Harmonics are the last title, last section we are going to discuss in this chapter. In fact, these harmonics are related to standing waves. We studied the standing waves in the previous chapter, chapter 3. Standing waves sound produced by the standing waves. We should first know this. A variety of standing waves can occur when a string is set into vibration. This vibration on the string consists of many standing waves together at the same time. And when you strike a string, so in this string there will be formed some standing waves. These standing waves will produce this sound. So the sound you hear from a string instrument, even those that sounds like a single pitch and like a single frequency, actually consists of multiple frequencies. So several possible vibrations form on an ideal standing waves. So if a string is fixed board end, so this end becomes note because not vibrating, each end is note. Between these two notes there are antinodes and notes, different number of antinodes and notes. Standing waves on a vibrating string generates the sound. We explained this before, but to form the standing wave on a string, so we should vibrate the string at some specific frequencies. So standing waves cannot be observed, cannot be generated at every frequency. At certain frequencies you can produce it at certain wavelengths. So the frequencies which forms a standing wave on a musical instrument, it can be a string, is called harmonic series. The first standing wave, remember, was just one lobe. This one, in this case, length of the string is equal to lambda over 2, and 0.5 lambda 1. Remember, we said that each lobe has a length of 0.5 lambda. So then L is equal to lambda 1 over 2. When you cross multiply them, so it becomes, if you continue to, instead of lambda 1, if you write V divided by F1, because we know that V is equal to lambda times F. So in this case, lambda is equal to V divided by F. Why are we doing this? Because we are going to explain the harmonics in terms of frequency. Instead of lambda, we wrote V divided by F1. Then simply cross multiply them, F1 becomes V divided by 12. So this is the smallest frequency which produced the standing wave on the string. So no more standing waves available on the string. So this is the smallest frequency. For that, the smallest frequency is known as the fundamental frequency. So second one is, as you see, there are two loops in the second standing wave. It is called second harmonic. Length is equal to 1 lambda because there are two loops, 0.5 lambda. So 0.5 lambda, when you add them, it becomes 1 lambda. Length is equal to 1 lambda. So then lambda is equal to, remember, V divided by F, V divided by Ft. Why did we say Ft? Because it's the second harmonic. For second one, F2, we are going to say that. F2 becomes V divided by L. So as you see, F2 is twice of that number. So if you multiply fundamental frequency by 2, you will get the second frequency of the second harmonic. So third one has 3 loops, 1, 2, 3. Each has a length of 0.5 lambda. 0.5 plus 0.5 plus 0.5 is 1.5 lambda 3. So then lambda 3 is equal to V divided by F3. It is the frequency of the third harmonic. So by using this frequency, you can form that standing wave. F3 becomes 1.5 V divided by L. As you see, frequency of the third harmonic is 3 times of that number. If you multiply the fundamental frequency by 3, you will calculate the frequency of the third harmonic. And the fourth one also, it is 1.0.5, 0.5, 0.5, 0.5. It becomes 2 lambda. Length is equal to 2 lambda. So length is equal to 2 times V divided by F4. F4 becomes 2 multiplied by V divided by L. So as you see, this is the 4 times of that fundamental frequency. So then harmonic series changes like this. Fundamental, if the first harmonic has a frequency of F1, second harmonic will have a frequency of F2, which is 2 times F1, third harmonic will have a frequency of F3, 3 times F1, fourth harmonic has a frequency of 4 times F1. Give a number. Assume that initially fundamental frequency is 100 Hz, second harmonic will have a frequency which is 200 Hz, third harmonic will have a frequency as 300 Hz, fourth harmonic will have a frequency as 400 Hz. So, can we write the general equation? Yes, we can, right? Harmonics are, as you see, integral multiples of the fundamental frequency. First, second, third, fourth, so 2 times, 3 times, 4 times. So if you write n as the number of harmonics for second, third, your equation will be Fn is equal to n times V divided by 2L. When you look at this equation, two things determines the frequency of the harmonics. One of them is the speed of the wave in the string. Second one is the length of the string. So why is it important? Because when you play a guitar, generally you press your fingers over the string and you make the string length grade shorter and longer. If you make the string length shorter, as you see, frequency increases. If you make the length of the string by removing your fingers up, so you are going to make the frequency of the harmonic smaller. Also, speed of the wave can change the frequency. Speed of the wave means, how can you change the speed of the wave on a string? By stretching the string, you can change the speed of the wave. Yani stretched string, the wave becomes greater. So then, if speed of the wave is greater, also fundamental frequency increases, and frequency of the sound also increases. This is important because generally it's confused. This V is the speed of the sound. No, it's not speed of the sound. It is the speed of the wave traveling over the string. So V is the speed of the wave on the vibrating string. It is different from the speed of the sound in air. So if the string vibrates at one of these frequencies, the sound wave produced in air will have the same frequency. Yani sound will have the same frequency of the harmonics. If this is 100 Hz, you are going to hear a 100 Hz sound. Of 200, you are going to hear a 200 Hz sound. So harmonics also possible. You can form the harmonics also in the air column. So what does air column mean? It's a tube. You can blow a tube and you can make a sound like the flute or like a trumpet or saxophone or any other instrument. You blow, but you can produce sound by blowing. So how is it possible to produce sound in a tube? While somewhat waves, when you blow it, you produce the vibration at one end. So the waves are traveling over along the tube and forming standing waves. This standing waves produces the sound. So there are two types of tubes we are going to study. One of them is tube open at both ends. As you see, here is open, there is open. You blow it here, then you make the sound. So the waves in the opposite direction combine to produce standing wave. Remember, when one of them is going down, reflecting back, coming back, so when they form the standing waves and produces the sound. So when this reflecting end of the pipe is open, the air molecules have complete freedom of the motion, so they can freely vibrate right here. So an antinote exists. Yani at open end, antinodes exist. Thus each end is an antinote. Here is antinote, there is antinote. Between two antinodes, there is one note. As you see, here is antinote, so again note, antinote. So open end, again antinote. So as you see, note, antinote, antinote, it goes on like this. So as you see, number of antinodes is one greater than number of notes. But in the string, it was vice versa. In the string, remember, fixed at from two end, it was note, and with the middle one, antinote. So here is vice versa, antinote, and note. However, length of the tube is the half wavelength. So this is a quarter lambda, 1 over 0.25 lambda. This is also 0.25 lambda. When you add them, you get lambda over 4. So that distance is lambda over 2. Lambda over 2. So then length of the tube is equal to lambda 1 over 2. Then you go on the same way. Lambda is equal to V divided by F1. So then cross multiply them. F1 becomes V divided by 12. It is the same as the string. In the string, the first standing wave also formed with that equation, V divided by 12. Yani equation for fundamental frequency, which is the smallest frequency which forms a standing wave which produces a sound, is the same as the string, V divided by 12. But for the second harmonic, again the second harmonic is twice of the first harmonic, again the third harmonic is 3 times of the first harmonic, and so on. And general equation for open-end board and tube is the equation Fn is equal to n times v divided by 2L is the same as the string, n is equal to 1, 2, 3, and so on. So according to the equation, two factors determine the frequency. One of them is speed, again, speed of the wave inside the tube. This depends on the medium which is the wave is traveling. Second one is the length of the vibrating air column. So remember, in the tubes there are openings, some openings. When you close them, these openings in the it can be fluid or another instrument, you are making the length increasing. If you close this one, length increases much more. If you close that one, length increases much more. And then finally, as you increase the length, so frequency of the sound in this case will decrease, or vice versa. A flute is a similar instrument to pipe open at both ends. Another type of instrument is the instrument or pipe closed at one end. Now, this, as you see, this is a tube, but one end is closed. So, because end is closed, right here the molecules are not free to vibrate. For that, as in closed end behaves like a note. If this is not, open end is antinote. As you see, in closed end one pipe, there is one note, one antinote, or two notes, two antinotes, or three notes, three antinotes. So, in this case, length of the tube, that is the length of the tube, is equal to a quarter wavelength. This is a quarter wavelength, and lambda over 4. Then if you go on calculation, you are going to calculate the fundamental frequency for one end closed tube is V divided by 4L. Remember, in open at board end, it was V divided by 2L. Yani, the fundamental frequency of the one end closed pipe, half of the two end open pipe. So this is the first harmonic. The next one, the following harmonic, as you surprisingly, is not the second one. Yani in one end closed pipe, only odd harmonics are present: F1, F3, and F5. So F1 is V divided by 4L. F3 is 3 times V divided by 4L, which is 3 times the fundamental frequency. F5 is 5 times V divided by 4L, which is 5 times fundamental frequency. Seventh one, 7 times V divided by 4L, which is 7 times fundamental, and so on. And general equation for calculating the fundamental frequency for one end closed pipe is times V divided by 4L. Trumpets, saxophones, and clarinets are similar to pipe closed at one end. Okay, next title is this is the we are going to study is the sound quality or timbre. Remember, we said that each instrument produces sound by standing waves, but there are so many standing waves. For that reason, each instrument has its own characteristics, mixture of harmonics, and there are so many standing waves, so many harmonics, which mean, so when they mix, they make a sound. That sound is called sound quality or timbre. So, for example, for a tuning fork, it vibrates only its fundamental frequency. As you see, it is F1 at just one intensity. For that, its waveform is very simple. However, other instruments are not so simple. The mixture of the harmonics that produces the characteristic sound of the instrument is called sound quality or timbre. The harmonics add together and according to the principle of superposition to give the resultant waveform shown in the third column. Now look at here. This is the second harmonic, this is the third harmonic, this is the fourth harmonic, this is the fifth harmonic. So when there are so many harmonics for an instrument, when you add them, you are going to get a waveform which is complex, which is not so simple as the tuning fork. Why? Because the instrument has so many harmonics, and that's why waveform is complex. So what makes this enjoyable to listen to music? Because there are so many harmonics in a instrument, so then waveform becomes complex, and that makes the sound rich. But in a tuning fork, if you look at them, as you see, the waveform is very simple. For a very simple waveform, nobody wants to listen what a tuning fork all day long, but you can listen to music for a long time. So as you see, this is the waveform of tuning fork. As you see, there is just first harmonic, But for a clarinet, as you see, first, second, third, fourth, fifth, and seventh harmonic present. First and second one, especially third one, is the most intense harmonic. First one is second one, and then as you see at different intensities, the waveform is more complex. For a viola, first, second, third, fourth, fifth, and sixth harmonics are present at different intensities. The waveform is a little much more different. However, when we observe the waveforms, we see that the waveforms repeats itself. So it repeats itself too. So then we say that even though waveforms of clarinet is more complex than those of the tuning fork, note that each consists of repeating pattern. As you see, it's repeating. So such a waveform is said to be periodic waveform. So maybe I can make the generalization for an instrument. Mixture of the all harmonics at different instances produces timbre. So we can, by this way, we can understand which instrument, according to listening to their sound, we can understand what kind of instrument it is or which instrument it is. Next, in musical instruments, the fundamental frequency of the vibration typically determines the pitch. This is information, very important. Other harmonics are sometimes referred as overtones. For example, generally instruments are the notes are played between the first and second harmonic. So in chromatic musical scale, there are 12 notes between first and second harmonic. Between first and second harmonic, there are 12 notes. You start from do, re, mi, fa, sol, la, si, do. Then from now on, starting the the first overtone. Yani again do, re, mi, fa, sol, la, si starts, but it's another frequency. So then from fundamental frequency n is equal to 1 to n is equal to 2. So it is it's called 1 octave. But from second harmonic starting to first overtone, so another octave right here. Again, here is between these two, there is 12 notes. In the chromatic musical scale, it says that there are 12 notes. The frequency of the 13th note is exactly twice that of the first note. Now look at here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 note. So 12 is 13,868, but the first one was 16,352. So 13th will be exactly the 2 times of this number. Yeah, 2 times of 16,352 will be the frequency of the 13th note. So altogether, the frequency of the 13th note is exactly twice that of the first note. Together, all these is called 1 octave in musical literature. Now, last title is the reverberation. Reverberation, simply echo. We can say that echo. Rooms are often constructed so that sounds made by a speaker bounce back and forth against the ceiling, walls, floors, and other surfaces. This repetitive echo is called reverberation. So, ceilings in the library or other quiet places are often made of soft and textured material to muffle, to absorb the sound. Padded furnishing and plants can also absorb the sound and stops the reverberation or repetitive echo. So in radio studios, wall of the radio studios generally covered by sponges. Why? Because we want the sound to be muffled or absorbed, not to reflect. If it reflects, in this case, we cannot hear the sound clearly. Reverberation time is the amount of time it takes for a sound intensity to decrease by 60 decibel. For speeches, the auditorium is designed so that the reverberation time is to be relatively short. If it is not relatively short, in this case, sound, what speaker says cannot be understood very clearly. Sample problem. What are the first 3 harmonics in 2.45 meter long pipe that is open at both ends? If it is open at both ends, equation is Fn is equal to V divided by 2L. So we will find first 3 harmonics, which means F1, F2, and F3. So assume that the speed of the sound in air is 345. Speed of the sound in air, which means when you blow through the tube, so this is the wave speed, 345. So length is given, speed of the wave is given, calculate the first harmonic, second harmonic, and third harmonic. First one is easy, n is equal to 1, you are going to write it 1. 345 divided by 2 times L is known, so it is the frequency of the first harmonic. Second harmonic will have this twice of that frequency, 2 times 70, which is 140. third harmonic will have 3 times of that frequency, so which is equal to 3 times 70, which is 210. So if the end are closed at one end, in this case, what happens? If it is closed at one end, fundamental frequency changes, and we divide by 4L. In this case, only odd harmonics are present, 1, 3, and 5. For the fundamental frequency, we divided by 4L, it is 35. But next harmonic is not second one, it's third one, because only odd harmonics present in the closed at one end. 3 times of that number, 205. For the fifth one, the following, next one is the fifth one, 5 times 35, which is equal to 175 Hertz. And practice problem 1. What is the fundamental frequency of 0.2 meter long organ pipe that is closed at one end? So if it is closed at one end, and we divide by 4L is your equation. When the speed of the wave in the pipe is 342, it's the speed of the wave inside the pipe. Length is equal to 0.2 meter. Calculate the fundamental frequency. That is your equation. Simply you are going to write the numbers and you will find the answer. A fluid is essentially a pipe open at both ends. Yes. The length of the fluid is 66 centimeters. What are first 3 harmonics? So open at both ends. So this is the equation. First 3 harmonics means F1, F2, and F3. We will calculate them because all harmonics are present in the fluid. Open at both ends. Making the vibrating column approximately equal to the length of the fluid. The speed of the wave in the fluid is 340. So 340 is the speed of the wave in the tulip. It is the length of the fluid. We will find what F1 is, what F2 is, and what F3 is. So first calculate the fundamental frequency, and we divide by 2L. N is 1 for fundamental frequency, V is 340, 2 times L is 0.66, this is the fundamental frequency. Second harmonic will have this 2 times of that number, which is equal to F2 is equal to 2 times of 258. F3 is 3 times of that number, which is 774 Hertz. A violin string is 50 centimeters long, so has a fundamental frequency of 440 Hertz. What is the speed of the wave on the string? This time they are asking about the speed of wave because it's the fixed at both ends. It's that string. It's the equation for calculating the Harmonic Series, and we divided by 2L. Length is given as 50 centimeters, which is 0.5 meters. So fundamental frequency is given F1 is equal to 450 Hertz. Calculate the speed by using this equation. F1 is equal to V divided by 2L. For calculating V, cross multiply them. V is equal to F1 times 2L. F1 is given 2 times L. Then you multiply them. Answer becomes. On a piano, the note middle C has a fundamental frequency of 262 Hertz. What is the second harmonic on this note? Because it's a stringed instrument, all harmonics are present. Second harmonic is equal to F2 is equal to twice of the F1. So 2 times of F1, which is 524. If the piano wire in item 1 is 66 centimeters long, so what is the speed of the wave? Equation is for fundamental frequency V divided by 2L. Cross multiply them, we will find the speed. V is equal to F1 times 2L. F1 is given in the question 1. L is given. To multiply them, you will get the speed of the wave. In a clarinet, the reed end of the instrument acts as a note because by using your lips you close the one end of the clarinet, so it is closed at one end. So the first open hole acts as an antinote. Because the shape of the clarinet is nearly cylindrical, its harmonic series approximates follows that of the pipe closed at one end. Yes, what harmonic series is predominant in the clarinet? Because it's closed at one end. So only odd harmonic series are present. 1, 3, 5, 7, 9, 11. Which of the following must be different for a trumpet and banjo when notes are being played both at the same fundamental frequency, which means their frequencies are equal. And they have the same fundamental frequencies. It says they are equal to each other. So, because first let's start from different one. Because these instruments are different, their timbres are completely different. If timbres are different, so they have different number of harmonics, because number of harmonics at different intensities produces different timbres. These two are different. What about the speed? Speed of the sound in air is the same, because sound of banjo and trumpet both are traveling the air, so their speed in the air will be the same. If their speeds are the same, question says their fundamental frequency also the same. According to the equation, lambda times f, if fundamental frequencies are equal, so if speeds are equal, wavelengths of the first harmonic also must be equal. Yani A and D are the same, B and C are different.